Probability. Some terminology now that we know how to do the sums, and some formulae in that. One of the technical terms they use is, the precise term they use is independent events. And an independent event, they talk about events being independent, one being independent of the other. In the case of two events, if the outcome of the first event does not affect the outcome of the second, then the two are considered independent events. An example, a deck of cards contains 52 cards. A card is selected at random, but is put back before the second is selected. The probability of finding a particular card on the second selection is not influenced by the first event, because you took it out and you put it back in. A deck of cards contains 52 cards. A card is selected at random and put back before a second card is selected. What's the probability of getting a club followed by a red card? So the first one you do is you want to get a club. The second one, you want to find a red card. But it's not like you left the club out, you put the club back in. So what's the probability that the first card is a club? Well, you say what P of club is. And we use the only equation we know, the total number of clubs over the total number of cards. So in this case, 13 over 52, or 1 in 4, because there are 4 suits. What's the probability that the second card is red? It's really important that the second one was put back. The first one was put back. So we're back again to 52 cards, and 26 of them are red, the hearts and the diamonds. So 26 out of 52 is 1 over 2. So we want this to happen, and we want the second thing to happen. So now we're looking at the formula that says the probability of a club followed by a red is P club and red card. So this is the probability of a club by the probability of the red card. And that's given by 1 over 4 for the club, 1 over 2 for the red card. We multiply 1 over 8. Dependent events are not independent by their very nature. In the case of two events, if the outcome for the first event affects the outcome for the second, the two events are dependent. Here we have a bag and it contains 3 apples and 3 oranges. If a bag does that, what's the likelihood of an apple selected on the first? Well, you've got 3 apples and 3 oranges. You pick a fruit at random, it's 3 out of 6. If the first fruit selected is an orange, and if it's not replaced, then the likelihood of the second fruit being an apple rises to 3 out of 5, because one of the oranges is gone. In this way, the likelihood of being selected depended on what was selected beforehand. So in your questions, you've got to figure out what happened first, and was it put back? Was it not put back? What's the story? So here we've got an example, and we say a bag contains 3 apples and 3 oranges. 2 fruits are chosen. That term is regularly used in the exams, without replacement. What is the chance of getting an apple followed by an orange? The probability that the first fruit is an apple is 3 over 6, because there were 3 apples and 3 oranges, so that's a half. What's the probability that the second is an orange, knowing that the first is an apple? Well, if we look at it, we can say orange 1, orange 2, orange 3, apple 1, apple 2, apple 3. And the first one was chosen, was an apple. So maybe we could take that one as an example. What's the probability that the second is an orange? Well, we have 3 here out of 5. So number of outcomes meeting the conditions over the total number of outcomes. So there are now 3 oranges remaining out of a total of 5 fruits. 3 of the fruits satisfy the condition. So it's gone up to 3 out of 5. Now, if we want the probability of an apple followed by an orange, we say this and this. So the apple first and orange after apple. Apple first is 1 over 2. The second one is 3 over 5. Multiply the two together. 1 by 3 is 3. 2 by 5 is 10. And that's that one there done. Another technical term they use is the term mutually exclusive outcomes. And outcomes are said to be mutually exclusive if they can't both happen at the same time. For example, when choosing a card from a pack, the card selected can't be both clubs and spades. It's a club, but then it can't be spades. It could be a club and a 5, but it can't be a heart and a diamond. So however, the card selected could be both a king and a black card. So you have to be very careful about this mutual exclusivity because it brings us to the question about OR. In cases of mutually exclusive outcomes, OR makes things easier and more likely. When things are mutually exclusive, like even numbers and 1 on the roll of a die, the probability of an even number or a 1 is the probability of an even number plus the probability of a 1. You can just add. It makes life easier. Higher probability. The special formula for use in this case is as follows. PA or B is PA plus PB. It's called a special rule because it doesn't apply all the time. It only applies if the things are mutually exclusive. You can't use it when they're not mutually exclusive. The general formula for OR is that in cases where outcomes are not mutually exclusive, OR can make things easier, but not necessarily. In these cases, the general formula which works in all cases is given by this. So that formula is the general rule, and you can use it even in the case of the special rule. It always works for OR. So PA or B is PA plus PB minus the probability of both A and B. So let's see if we can make use of that. What's the probability of, you roll a die and establish the probability of the following outcomes. What's the probability that you get an even number or a 1? Well, a 1 is not an even number. So those two events are mutually exclusive. We should be able to use the special rule. And let's see, and the other one is P odd number or a 1. Well, a 1 is an odd number, so they're not mutually exclusive. So we won't be using that. We'll use the general rule. We might use the general rules for both. The sample space for a roll of a die is given by 1, 2, 3, 4, 5, and 6. If we look at an even number or a 1 on the roll of a die, the outcomes of even and 1 are mutually exclusive. Using the special rule, PA or B is PA plus PB, where A is the word even, and B in this case is 1. So even or 1 is P even plus P1. Chance of it being even, 3 out of 6, because you have 2, 4, and 6. Chance of it being a 1, 1 over 6. Add the 2, 4 over 6. So what we know instinctively, we can now see that the equations work for us in that case. We do the same for the odd numbers, P odd or 1, and we say the outcomes here are not mutually exclusive. We use the general rule, PA or B, PA plus PB minus PA and B. Again, we're using the word odd for A and 1 for B. So P odd or 1 is P odd plus P1 minus P odd and 1. So there are 3 ways in which a number can be odd, 1 way in which it can be 1, and 1 way in which it can be odd and 1. So 3 over 6 plus 1 over 6 minus 1 over 6 is 3 over 6. So that's why the formula works there as well. Now, let's say we use the general formula for this case, the even or 1. What would have happened? Well, the general formula works every time. So it says PA or B is PA plus PB minus PA and B. So you'll say P even or 1 is P even plus P1 minus P even and 1. Now if we look at that, what's the probability of it being even? P even is going to be 3 over 6. What's the probability of it being P1? 1 over 6. And what's the probability of something being both even and 1? Is that possible? No, minus 0. 4 over 6. So we would get the same either way. It works in every case. Is that okay? The general rule. Now, if I turn to page, on the next example, card probabilities. A card is drawn at random from a pack of 52 cards. Find the probability that the card drawn is either a queen or a club. So we're seeing, we had done it before with sample spaces, but does it work in the formulae? Well, here we've got all of the clubs showing, and here we've got all of the queens showing, queen of clubs, spades, diamonds, and hearts, with the representations as before. The sample space shows 13 clubs and 4 queens. However, the queen of clubs is in both sets, because the queen of clubs is in the clubs set and in the queen set. We calculate the probability, the number of outcomes meeting the conditions over the total number of outcomes, but we're conscious of the Venn diagram. Here are the queens, 3 and 1. Here are the clubs, 12 and 1. And this one is both a queen and a club. So we know the answer is 16. What does the equation give us? Well, the equation says that, well, we are looking for both queens and clubs. So we're certainly, they do overlap, but we're certainly not sure they're mutually exclusive, because something could be a queen and a club. And to be sure, we're going to use the general rule for OR. So A or B is one plus the other minus both. So what's the probability of a club or queen? It's probability of clubs plus the probability of queens minus the probability of both. Well, the probability of clubs, there are 13 of them over 52. Queen, you have 4 over 52. And you have 1 that's both a club and a queen. That's the minus there. So 13 plus 4 minus 1 gives us the 16 over 52. So we now know that we can use this method with the formula confidently, because we've used it also in our own understanding and with the sample spaces.